I'm Keiji Miura. I will be talking about tropical neural networks and its applications to classifying phylogenetic trees. Some of the breakthroughs in machine learning have been triggered by introducing unconventional ideas from algebraic geometry. In fact, there are many fields that utilize algebraic geometry. Algebraic geometry is a central field of mathematics in which, in a narrow sense, polynomial equations are solved with the aid of algebra. It can be a great addition to analytic methods. In this paper, we attempt to utilize tropical algebra, which has tropical polynomials and other tropical counterparts, to classical algebraic geometry. Little application of tropical algebra in AI has been known until recently. Let me explain what is the tropical algebra. In the conventional mathematics or commutative ring, we use addition and multiplication as basic operations, of course. In tropical algebra, we change that rule. Instead, we use max and plus operations. For example, 1 tropical plus 1 equals 1 because the maximum of 1 and 1 is 1 classically. That is, a tropical sum is a classical max operation. Similarly, 3 tropical times 4 equals 7 because the classical addition of 3 and 4 is 7. This is why tropical algebra is called max plus algebra. It may take some time to get familiar with this new rule, but once you can describe your equation only with max and plus operations or with tropical polynomials, you can utilize many formulas from tropical geometry. We expect something good happens if equations are closed with only max and plus operations. This is analogous to the situation. There are many helpful formulas in classical algebraic geometry for classical polynomials. Our ultimate goal is to build a completely new mathematics one more time from the elementary school level with the 1 plus 1 equals 1 rule. One nice application of the tropical geometry is a neural network with ReLU activation functions, because ReLU can be described as the max of 0 and x, like this. The input-output function of the entire neural network becomes just a tropical polynomial, as we will quickly confirm in the next slide. As a conclusion, it was shown that the upper bound of the number of kinks or the linear regions in the boundary can be computed from the number of layers and neurons in a given neural network. For example, you can show how many layers are required to represent a given boundary. It is surprising you can predict the impossibility of learning before you train. They specifically found that adding a layer is much more efficient than adding neurons in each layer. This slide just briefly confirms that a neural network with ReLU is in fact a tropical polynomial. In the previous slides, the tropical algebra was used just as a tool to analyze the classical ReLU neural networks. Therefore, the input vector of a neural network was from the Euclidean space. However, there are spaces like a phylogenetic tree space that are more suitably represented with tropical distances. To utilize the tropical algebra fully or more natively, in this paper we construct a neural network that accepts an input vector from a tree space. A tree can be represented by a pairwise distance vector. In this example, d12 or the distance from node 1 to node 2 is 1, and d13 is also 1, and d23 is 0.5. This distance vector with the ultrametricity constraint is compatible with the tropical distance. Especially in this paper, we focus on the one vector invariance the tropical distance has. That is, a vector v is identified with v plus 111, as we will show next. Here is the definition of the tropical distance between two vectors v and w. In this example, it may be convenient to take the difference vector delta for the two given vectors. Then the max minus mean of the difference vector delta is what we want. The result a plus b is somehow similar to a Manhattan distance. Finally, it should be noted that adding one vector to v or w does not change the distance. Therefore, the tropical metric is invariant under one vector as desired. This slide formulates a tropical neural network we propose. In a word, we use the tropical embedding layer as the first layer of the classical neural networks to keep the one-vector invariance. The tropical embedding layer simply transforms a distance vector in the tree space to a vector in the Euclidean space via the tropical distance. Note that the weights W are added but not multiplied to an input vector. First, we wanted to know if a tropical neural network has enough expressibility, so we proved that a tropical neural network is a universal approximator. This is simply because the first tropical embedding layer can represent a coordinate function xj minus xn if the weights are tuned, and thus never lose information at all. Next, we write down the backpropagation rule in the first layer of a tropical neural network with one hidden layer. The learning rule in the second layer and later layers are the same as that of the classical neural networks. Thus, we hope this simple example suffices to illustrate the essence. We found that the weight updates in the first layer is sparse and only 2 of them are updated. We also described the distribution of the neural activities in the tropical embedding layer under the assumption of random weight initialization by using the extreme value statistics. Finally, we provided the TensorFlow2 code for implementing with GPUs a tropical neural network in the same fashion as the classical one. In the classification of full phylogenetic trees, the tropical neural network was less confused.